one that you should definitely try is the following. Here you don't really even need KKT, all you need is the A is nothing but trace of A star A, square root of that. Suppose Y is a symmetric matrix and I want to solve it given symmetric matrices L and U. So this is the matrix version of this problem here. But let's see, let's try to, we haven't so far talked about KKT for semi-definite, right? Because so far Lagrangian, KKT, etc., whatever I said, all of that happened in R to the n. And the semi-definite cone is not R to the n, it is a subset of that, but it's still different. But you can repeat pretty much the same thing. So let me just quickly maybe show you the crux of deriving Lagrangians, etc., for semi-definite, on the semi-definite cone. So now we are working with, say, matrix variables, trace of C times X, subject to trace of AI, X is BI, and X is semi-definite. So you can assume A and C are all symmetric matrices, okay? And we want to kind of create a Lagrangian dual for this problem. So one quick step that justifies why we construct the dual the way I will is okay, so let me write something, call it, I'll create a sort of pseudo Lagrangian for it. I'll write X as the primal variable. I can write, say, nu for the equality constraints. And for the matrix constraint here, the so-called structural constraint, I'll introduce a matrix Lagrangian variable. It's not yet shown how, but let's hallucinate one. Plus or minus, whichever way you prefer. Let's write it with minus if you want. Nu I trace AIX minus BI. Because remember in our standard form, the constraints had 0 on the right hand side, so I did that. Minus trace of Y times X. So the reason now we are using that, first, suppose P star is the primal optimal value, right? So suppose P star is primal optimal value. Do you agree that P star is bigger than L of X comma nu comma Y for all feasible X, nu belongs to R to the n, and Y being semi-definite? So we are just trying to see that what might be a reasonable way to create duality theory for semi-definite programming. And why does this work out? Well, if X is feasible, this guy disappears. X is semi-definite. Then why does this inequality hold? In fact, this holds for not just P star, it holds for any feasible X. Why does that hold? Because trace of Y times X is non-negative for when Y and X are semi-definite matrices. And that is the key property being used when constructing this Lagrangian. Without such an ordering property on that cone, we wouldn't be able to construct such a simple linearized Lagrangian for these guys. So it's just that super humble lemma that allows you to have a reasonable. So by following the previous style, ultimately you'll end up proving weak duality. Like we just follow the derivations that we did last time to derive weak duality. So similarly, you'll get weak duality even here. There is additional work required to derive. So let's actually first go through trying to get a dual for that. Almost done. So by maybe mechanics for you, the dual, I'll derive it by infimizing out over, and if you look at it, the whole thing is just linear in X. So it can descend very easily to minus infinity unless the correct things become 0. So this linearity and sublinearity, etc. relations, they are at play here. So you can then see that so the parts depending on X, if you put them together, they are sort of like C minus nu I AI minus Y, essentially trace of that times X, right? That's the part depending on X. I just collected them together. So this initial multiplier had better be 0 to prevent us from descending to minus infinity, which then gives us that g of nu comma y, collect the parts depending on nu, minus of b is b transpose nu. If c minus sigma I nu I ai minus y is 0, otherwise it's minus infinity. So that's your dual. And you're trying to maximize the dual, so the dual's finite domain. I'll have to go back towards this side. So we are essentially done. So you get the dual optimization problem will be then maximize B transpose nu such that, what was it, C minus, okay, nu I ai minus y is equal to 0 and y is bigger than equal to 0. So you can eliminate that extra slack. Y is like, now you can actually eliminate that. This will boil down to then C minus nu I ai being bigger than equal to 0. You can get rid of that. So you get so-called conic form of the SDP. And at this point, I encourage you to look at, say, the last 2 pages of chapter 5 of Boyd and Vandenberge, and also do exercise 5.44. They establish a nice connection between primal and dual of semi-definite programming. I don't have time to go into that, but it's worth mentioning. For the world of linear programming, as soon as you're feasible, either in the primal or the dual, strong duality holds. But for semi-definite programming, you need strict feasibility of either the primal or the dual. And this is proved, you can say, in exercise 5.44. Half of this part is proved in 5.44, and half of it is proved in the last 2 pages or in chapter 5. And Laszlo Lovász has very nice lecture notes on his website where he discusses semi-definite programming and how to use semi-definite programming. This is a classic set of lecture notes by Laszlo Lovász on how to use semi-definite programming for relaxing hard discrete optimization problems. He has several very nice examples in there. In case you're interested, just Google for that and you'll find that. And one thing that I wanted to mention,
What is strict feasibility?
so it's like that, remember that Slater condition that once you have, so that would mean you would require a strictly positive definition. So there has to be some feasible guy in the strict interior of your constraint set for the constraints that are nonlinear. For linear constraints, you don't need, means this is an equality, it is already strict in some sense. Yeah, so that's what it means. One thing before we leave I wanted to mention, which we might exploit later if we work with large scale SDPs, is, so here again as usual in my convention there are m constraints and X is now an n by n positive definite matrix. So there is a theorem by Barvinok which says, under some small technical assumption, if the primal SDP is solvable, then, so if this particular formula, if this is solvable, which means doesn't become minus infinity or is not infeasible, etc., then there exists a solution x bar such that the rank of x bar, let's call it R, satisfies R into R plus 1 by 2 is less than equal to m, where m is the number of constraints. And so at this point I should mention to you where this has been exploited to build one of the popular and successful semi-definite programming solvers. So you should definitely read. Again, I mentioned reading assignments, it's for everybody, but probably the interested ones amongst you will definitely read that. So you can read where this is exploited, this simple low rank connection, in a famous paper by Burer and Montero called a non-linear programming algorithm via low rank. And this rank condition, etc., has been recently used by others to try to come up with large-scale semi-definite programming solvers. So far, this today is in some sense the last theory part. After that, whatever I will speak will be algorithms. But because so far we haven't looked at any algorithms to solve any of the problems that I mentioned. And this paper and some other recent work, people have exploited this geometric structure or the limitation on how large the rank of your SDP solution can be to obtain solvers that scale to very large SDPs. Because the standard ones like in CVX using Sedumi, DSDP, etc., they will choke after few thousand variables. So
How large is very large?
So it depends. So if this matrix is n by n, so the number of variables is n square essentially, n square by 2. So it depends on whatever fits into your computer. But so these days I think you can usually handle stuff with n equal to 5,000 reasonably easily. But after that it starts crawling because it takes substantial time to do any eigen computation, etc., with larger and larger matrices. But if you have a big enough computer, you can still maybe even tackle 10,000 by 10,000 dense matrices these days. But after that, it starts choking already. Yeah. So okay. So one of the projects that I have in mind is for those of you who care about software, is really building a large-scale SDP solver. So that will have to depart a little bit from what theory allows you, but it will be a very useful tool. But it's for those who care about the software part. There's some theory involved to actually justify the steps, but anyhow, that's one of the projects. Yeah.
No, I just wanted to ask you to what extent will be going into solving SDPs?
Just to know that they can be solved, and from, like I said, we will, when I look at large-scale optimization methods for general convex optimization. Some of those you might think about saying, what do they mean for SDPs? Can you do something with them? So they will apply, and I don't know if Alex wants you to actually then solve very large SDPs. There used to be a competition who can solve the largest relaxation of max cut. And for many years, this solver by Burer and Montero was the guy who was solving the largest instances. But there's been too much work done in that. Yeah, okay, I guess that's about it, what I had to say for today. So it took 10 minutes more than planned, but I'll see you maybe, I don't know, in 3 to 4 weeks.